Okay, hello everyone. In a new video, in this one we are going to start a new chapter, which is chapter 3, which is the electric current for grade 10 students. Then let me write down the title of the chapter. And let me directly start with section number 1, which is the electric current. For this reason, let's consider a simple electric circuit consisting of a battery, say for example, a lamp, and a resistor R, and K is an open switch. So now we know that this circuit is an open circuit. So we can talk about the voltage across the battery and the switch. So the voltage of the battery, say for example, it's 12 volts, and an open switch in series with the battery have the same voltage of the battery. Now the moment we close the switch, we know that this circuit will be traversed by a current I. So this closed circuit is being traversed by the current I. And the direction of this electric current is from the positive pole to the negative pole. So let's say any closed circuit or a closed circuit, let's say, more convenient, including a generator G, is being traversed by a current I. If this generator is of a DC voltage source, then the direction of the electric current is from the positive pole to the negative pole. So in this case, because the generator G is a DC voltage source, so the direction of the electric current is simply from the positive pole to the negative pole. In the case of an AC voltage source, the direction of the electric current is not constant. It changes with respect to time, because we know that the sign of the AC voltage changes from positive to negative, negative to positive across each half a period. Okay, so this is it for the electric current in a closed circuit. Now let me make also the following note. So this is idea number 1. So let's say idea number 2. In the case of a complex electric circuit, consisting of several generators and branches. The direction of the electric current can be always determined by calculating the potential difference U across 2 points, taking into consideration that the electric current traverses a branch from high potential into a lower potential. So suppose in this case we have a branch AB. Across this branch we have an electric component D. So suppose that this is the point A and this is the point B, across an electric component D, and we know that the voltage UAB is positive, which means that the potential at the point A minus the potential at the point B is positive, which means that the potential at the point A is greater than the potential at the point B, which means that the electric potential across this electric component or the electric current traverses this branch from A to B. Okay? Because always the electric current traverses a branch from a point of higher potential into lower potential. Okay, from high potential into a lower potential. So this is it for the first section. Now let's move to the next section, which is the laws of currents. Then let me write section number 2, laws of current. And let me start by the first one, which is given by section 2.1, the law of uniqueness of currents. Then let's say 2.1, law of uniqueness of currents. Then in order to explain this law, let's consider the following electric components that are in series. So let's say that this is the electric component D1 and this is the electric component D2. Now suppose that the electric component D1 is being traversed by the current I1 and the electric component D2 is being traversed by the current I2. But notice that because these two components are in series, let me say that D1 and D2 are in series. So because these two components are in series, so they have this terminal only in common. So completely the current I1 traversing this terminal of D1 is connected to this terminal of D2 and there is no leakage of current. So the current of I1 is completely transferred to D2. Therefore, for this reason, the value of I1 is equal to the value of I2. So whenever we say equal, this is mean the law of uniqueness. And then let's say according to law of uniqueness of currents, they are traversed by the same current. And in this case, we have that the value of I1 is equal to the value of I2. Okay. And now let's proceed to the second law, which is 2.2, the law of addition of currents. So now let's consider the following grouping. So suppose here we have electric component D. So suppose that this is the point A and this is the point B. Now let's suppose that the point B splits into 2 points or to 2 terminals. Now here we have the electric component D2 and here we have the electric component D3. And this is the point C. Now suppose that the electric component D1 is being traversed by current I1. So we can say that I1. Now the electric component D2 is being traversed by the current I2. And D3 is being traversed by the current I3. So it's very natural that we say that the current IY at the point B splits into 2 currents and are given by I1 and I2. So it's very natural to say that I1 is equal to I2 plus I3, and this is a law of nature. For this reason, this is given by the law of addition of currents. So apply, or this is given by the law of addition of currents. So, and we can apply this law of, also in more complicated situations like the following. Suppose here that we have, so let's consider the general case. Suppose that we have a node or a terminal A, and suppose that A is given by several branches. So this is the point A, and suppose here that we have current I1, current I2, current I3, current I4, current I5. So notice that now in this case, the currents that are entering the point A are given by I1 and I2. So we say that I1 plus I2 is equal to the current leaving the point A. So what are the currents leaving the point A? I3, I4, and I5. So how do we know that these currents I3, I4, and I5 are the currents leaving the point A? Simply because these arrows are pointing away from the point A. So this is equal to I3 plus I4 plus I5. So in this case, the law of addition of currents can be generalized into the following law. The summation of the currents entering a node is equal to the summation of the currents leaving the node. Okay? This symbol sigma stands for the sum, and this law is said to be the law of addition of currents. So always on the left we'll place the sum of currents entering a node. How do we know that these currents are entering the node? Simply because these arrows are pointing toward the point A, and on the right hand side we will write the sum of currents leaving the node. How do you know that these currents are leaving the node? Simply because this arrow is pointing away from A, and this will give us a linear equation and one unknown. The unknown is one of these currents. Okay, so each time we apply this equation into a node, it will yield to a one equation and one unknown. Okay, now let me move to the next section, which is reading the current using an ammeter. So let me write down section number 3, the ammeter. And let me give the symbol of the ammeter. So the ammeter carries the label A, and one of the terminals is labeled by COM. Now idea number 2, the ammeter. Now from its name, meter indicates an instrument that measures a current. So is an apparatus which measures the current across a branch of an electric circuit. Now idea number 3, the ammeter has two terminals. So idea number 2, I'm saying that the ammeter is an apparatus which measures the current across a branch of an electric circuit, because if the circuit consists of several branches, we know that each branch will be traversed by different electric current, and this is reasonable from the law of addition of currents. So the ammeter has two terminals and it must be connected in series. So why the ammeter must be connected in series? Because according to the law of uniqueness of current, the current is the same, so it needs to measure the same current. Now if the COM terminal is connected to the negative pole, then the ammeter measures, it's always the opposite, because it's connected to the negative pole, then it measures positive reading. Now let me write idea number 5. Is connected to the positive pole, then the ammeter measures negative reading. Now idea number 6. There is two types of ammeters. The first is given by the digital ammeter. So it measures current by displaying numerical value. And 6.2, there is the analog ammeter. Measures current by the deviation of the needle. And now let me move on to section number 4, is using analog voltmeter. Sorry, ammeter. Let me make sure here everything is okay. Using an analog ammeter. And let me say that the current measured by the analog ammeter is given by I is equal to S multiplied by D divided by capital D. It's exactly the same that the voltage measured using an analog voltmeter, but instead of U, it's given by I, since this is given by an ammeter. Now let me define each quantity. What does it refer to? So let me say where I is the current measured by the analog ammeter, and its unit is given by amperes. Its symbol is A. S, small s, is the scale, or range, which is given by A amperes. Now small d represents the deviation of the needle, so in div, which stands for divisions. And finally capital D, which stands for is the dial or range, real or total range is for the scale is the total number of divisions expressed in div, which stands for divisions. And now let me mention also what is meant by the convenience scale. Although we have mentioned this in the previous chapter, let me say the following important note, that the most convenient scale is the one having a scale slightly larger, slightly greater, than the value to be measured. So this is it as an explanation for this chapter. Yet we need to discuss the charge carriers, and this is left for the coming parts. Now let's solve the following exercise as a direct application on what we have explained. So in this case, in each of these figures we have a node or branches connected to a node. So we can say, for example, that figure A is given by node A, this is node B, this is node D, and this is node C. So these are branches connected to the nodes. So for each node we have connected branches that correspond to a larger part of an electric circuit. Now in each figure we need to determine the missing current. So let's start by figure A. And it is convenient to label these currents. So let's say that this is the current I1, this is the current I2, this is the current I3, and the missing current is given by 4. So notice that in each figure there is only one missing current, because as supposed here we should apply the law of addition of currents, and the law of addition of currents only allows us to determine one unknown. Okay, so as for figure A, let's apply the law of addition of currents. So always in physics we need to mention the law that we are using. So for this statement usually they give us half a mark. So we'll say that the summation of I in is equal to the summation of I out. So on the left hand side of this equation we'll write the currents that are entering the node, and this can be determined by referring to the arrow. So notice that this arrow is pointing into the node, so it's given by I1. As for this current, this current, this current, all of them are pointing outside the node, so they are given by I out, so I2 plus I3 plus I4. Knowing that we are interested in I4, so we keep it as a variable. The value of I1 is given by 5.2, the value of I2 is given by 3.3, and the value of I3 is given by 1.8, and I4 is kept an unknown. So what's the type of this equation? This is a linear equation. One unknown, the unknown is I4, so we will put I4 on one side and all the other numbers on the other side. Then solving for I4 and plugging this complicated expression on the calculator, then the value of I4 is given by 0.1 amperes. Then I4 is equal to 0.1 amperes. So this is it for figure A. Now let's move to the next figure, which is figure B. And let me label the following currents. So suppose that this is I1, this is I2, this is I3, and this is I4, and this is I5. And for sure we need to apply the law of addition of currents. Apply law of addition of currents. So always in physics we need to mention the law that we are using, so usually this give it half a mark. So summation of I in is equal to summation of I out. Now on the left hand side of this equation we'll write the currents entering the node. So notice that I1 is entering because the arrow is toward the node. This is leaving, leaving, leaving. Notice that I5 also is entering. So we have I1 plus I5. And all other currents are leaving the node, which are given by I2, I4, and I3. And we are interested in determining the value of I5. So in this case, I1 is given by 2.7, I5 is kept as a variable, I2 is given by 1.4, I4 is given by 1.6, and I3 is given by 3. So what's the type of this equation? This is a linear equation and one unknown. The unknown is I5. So how do you solve it? We put I5 on one side and all the others on the other side. So 1.4 plus 1.6 plus 3 minus 2.7. Plugging this expression on the calculator, then the value of I5 is given by 3.3. Since all of these quantities are expressed in amperes, so the value of I5 is an ampere. So I5 is equal to 3.3 amperes. Now finally for figure C, also we need to apply the law of addition of currents. Then for this statement they give it half a mark. So we say summation of I in is equal to summation of I out. Let's label the currents. So this is I1, I2, I3, I4, and I5. So on the left hand side of this equation we'll enter the currents entering the node. So I3, I5 is entering the node as well as I2 because these are pointing toward the node, whereas I1, I3 and I4 are leaving the node. So I2 plus I5, so this is 1, 2, 3, 4, this is 5, let me make it clear. Now as for the leaving the node, we have I1 plus I3 plus I4, knowing that you are interested in determining I3, so it's kept as a variable. What's the type of this equation? Linear equation and one unknown. I2 is 7.3 and I5 is given by 2.3, which is equal to I1, which is equal to 3.8 plus I3 plus I4. The value of I4 is given by 1. Let me double check again 2.3 I5, 2.3 I1, 3.8. Okay, so I3 is simply given by 7.3 plus 2.3 minus 3.8 minus 1. So this is equal to 4.8 because everything previously is expressed in the SI, which is amperes, so the value of I3 is amperes. So this is it for this exercise and for this video, guys. In the next part we'll complete solving exercises and explanation of this chapter.